Okay, so today we're going to talk about more about conditional probabilities. So the probability that an event will occur given that some other event has already occurred or is certain to occur is called a conditional probability. An example would be the results from a market survey indicate that 39% of the customers surveyed believe a product is of high quality. However, if the analysis is limited to only women, 54% of the women surveyed believe that the product is of high quality. Based on that survey, it appears that women have a much higher regard for the company's product than men. The difference in attitude would probably be something that would affect how the company spends its marketing dollars. So, probability law number 9. Last class we started going through probability laws. This is number 9. The conditional probability of event A occurring given that event B has already occurred looks like this. This little line right here represents the word given. So this is the probability of A given B. So to find the probability of A given B, you would take the probability of A intersection B divided by the probability of B. Okay? So with that in mind, let's look at number 1. Suppose a marketing research firm has surveyed a panel of consumers to test a new product and produced the following cross-tabulation indicating the number of panelists that liked the product, the number that did not like the product, and the number that were undecided. So the market research survey, we split it up into ages, 18 to 34, 35 to 50, and over 50, and then if they liked it, they didn't like it, or they were undecided. And here are the results, and I've already given you the totals. How many total people were surveyed? Yeah, 1,403, good. If an individual is between 35 and 50 years old, what is the probability that he or she will like the product? So, when you look at this table, you could probably answer that question without all of this hubbub. But the purpose of this is showing you how to correctly write this situation. So, if an individual is between 35 and 50, what is the probability that he or she will like the product? What that means is, what is the probability that a person surveyed likes the product given that that person is between 35 and 50 years old. Okay? So, the probability that the person surveyed likes the product given that that person is between 35 and 50 years old. So, comparing this to the formula that was given up above, we would have the probability of A given B, which means that this would be my event A and this would be my event B. Now again, that formula you have on your paper, I don't have on my screen, so I'm going to write it down quick. Probability of A given B equals the probability of A intersection B divided by the probability of B. So let's first find the probability of A intersect B. So I want to find out where the person surveyed likes the product intersects with the person between 35 and 50 years old. Do you guys see that somewhere? 193, right? But we need the probability of that. So the probability of A intersect B is actually 193 over that total of 1,403. Okay, that's the probability. Then we need to divide that by the probability of B happening. Now the probability of B was just that the person is between 35 and 50 years old. What was the probability that a person was between 35 and 50 years old? 444 out of my total of 1,403. And what we need to do according to this formula is we need to take my first probability and divide it by my second probability. So to do that, I'm going to take 193 over 1403, and I'm going to divide that by 444 over 1403. Now, quick question. Do you think I'm allowed to do that? No. Instead, what do? Multiply by the reciprocal. So 193 over 1403 times 1403 over 444. What do you notice right off the bat? It cancels out. The 1403s cancel out, and I'm just left with 193 over 444. Now, that was the exact formula, and just a reminder, you do get formulas on the test, okay? You just have to know how to use them. But now I want you to use a little bit of logical thinking here, okay? Let's use a little bit of logical thinking. The probability that a person surveyed liked the product, given the person is between 35 and 50 years old, ended up to be 193 out of 444. Where did those numbers come from? Yeah, look at the table. The probability that the person surveyed likes the product, given that the person is between 35 and 50 years old, likes the product, given that they're 35 and 50, that's 193, and we're only focusing on the persons between 35 and 50 years old. That's where the 444 comes from. Are we okay with that? All right, now at this point, I have full confidence in your ability to put that into your calculator and get a decimal. I don't think we need to do that. Let's move on to the next one. Out of 300 applicants for a job, 212 are male. Of the male job applicants, 110 have served in the military. What is the probability that a randomly chosen applicant has served in the military given that he is male? So again, we're going to say, what is the probability that an applicant served in the military given that he is male? So it's specified, out of 300 applicants for a job, 212 are male. Of the male job applicants, 110 have served in the military. So given that he was male means that my denominator is going to be just the males. How many males did we have? 212. Now, out of those males, how many served in the military? 110. That's it. That's all we have to do. Let's simplify it a little bit. What goes into both of those? 2, so that would be 55 out of 106. And there you go.
So basically that's the beginning of math, like part of it.
So sometimes the math, like the formula, all of this stuff, sometimes that's really, really helpful when the information is hard to follow. But on ones like this, no, you really don't. Yes?
Do you want us, if our test on paper?
No, your test is on both Excel and Canvas.
Okay, so when are we putting it in? Do you want to put it in the percent or fraction?
You can actually put it in as either.
Okay.
All right, letter B. If 152 of the applicants have served in the military, what is the probability that a randomly chosen applicant is male, given that the applicant has served in the military? So this is almost backwards. So this time they say, what is the probability that they're male, given that they have served in the military? Now my denominator this time is going to be how many served in the military. And how many did they say? 152. So out of those 300 applicants, 152 of them have served in the military. But out of those 152 that served in the military, how many of them were male? – 110. Up here it said 110 have served in the military. Because it's, sorry, up here it specified of the male job applicants, 110 served in the military. So out of the ones that served in the military, the 152, it specified 110 were men. So we can simplify that to 55 over 72. 76, sorry, 76. Get it together, guys. How do we feel about this? Show me your thumbs. Good. All right, number 3 is not yet. Next thing we're going to talk about is independent events. Now, we kind of introduced the concept of independent events last class when talking about mutually exclusive, but this is a little different when talking about conditional probabilities. So, this one says 2 events are independent if and only if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B. And that leads me to the probability law number 10. If 2 events, A and B, are independent, then the intersection of those 2 events is just the probability of A times the probability of B. If there are n events, remember n is some number, it could be 10, it could be 100, it could be 3, then my first event, second event, all the way to whatever event that I have, if those are all independent, then the probability of all of their intersections is the multiplication of them all. So, here is what intersection means, okay? Intersection is an and statement. Do you guys remember last class that we talked about how or was a union statement? Or was a union statement, and we did a lot of addition with those. And is an intersection statement, and we do multiplication with those. Now, if they are independent, we just multiply them all together. So, let's talk about an example. A really good example of an independent event would be rolling a die 2 times. And here's what I mean by that. The first roll is independent of the second roll. It does not have any impact on it, okay? If you roll a 2 on the first roll, that does not change what you're going to roll in the second roll. So, a good example means the occurrence of one event does not affect the occurrence of another event. Again, if you roll a 1 the first time, that does not affect what you're going to get the second time. You could roll a 1 again. You could roll a 2. You could roll a 5. It does not have any impact on it. Okay, so let's go to the back side. Number 3 says, a coin is flipped and a fair die is rolled. Find the probability of getting a head on the coin and an even number on the die. When you see the word and, that means we're going to be dealing with intersections here. Okay? Now, flipping a coin and rolling a die, are they independent events? Does one have any impact on the other? So they are independent events. So, here's what we're going to have to do. We're going to say the probability of getting ahead intersecting, because it's an even number on the die. Okay? Since these are independent events, to figure out what this probability is going to be, you're going to take the probability of tossing a head and multiply it by the probability of getting an even number. Okay? That's what probability law 10 states. Since they're independent, you just multiply them together. Now, when tossing a coin, what is the probability that you will receive a head? 1 out of 2, right? You can get heads or tails. Probability of heads is 1 out of those 2. When rolling a die, what is the probability that you will get an even number? 3 out of 6. Very good, because there's 2, 4, 6 out of 1, 2, 3, 4, 5, 6. And then you just multiply those together. So 1 times 3 is 3, 2 times 6 is 12, 3 out of 12 is 1/4. So the probability of getting ahead on the coin and an even number on the die is 1 out of 4. You have a 25% chance of that happening. Number 4, a coin is flipped, a die is rolled, and a card is drawn from a deck of 52 playing cards. What do we think? Independent events or not? Yeah, they're all like disconnected. Find the probability of getting a tail, rolling a 5, and drawing a jack of clubs. So, again, we're going to have the probability of getting a tail, rolling a 5, and drawing a jack of clubs. I can't really draw clubs, but I'm going to do my best. Mathematicians are lazy. That kind of looks like broccoli. Mathematicians are lazy, so we know what that means. I didn't even write the word roll. Like, what did I write? Oh my gosh. Whew. Rolling 5. Okay. So, if you'll notice, when I'm writing the probability, I'm writing it in a way that makes sense to me. You could write it as T intersect 5 intersect J C, jack of clubs. Like, it's literally like what makes sense to you. Does that make sense? Now, since these are all independent events, we just need to figure out the probability of each and multiply them together. So what's the probability of flipping a tail on a coin? 1 out of 2. Very good. What's the probability of rolling a 5 on a die? 1 out of 6. Awesome. What's the probability of drawing a jack of clubs? There's only one jack of clubs, so 1 out of 52. Very good. Now we just multiply these all together. So 1/2 times 1/6 times 1 out of 52 is going to be 1 out of 624. Again, you guys can put this into your calculator and get a decimal if you want, but I have full confidence in your capabilities at this point. Without even seeing what that is as a decimal, do we think this is likely or unlikely? Yeah, super unlikely. All right. Number 5. Next, choosing 2 cards from a standard deck, replacing the first card and shuffling before choosing the second one. What is the probability of choosing a king, then a queen? What do we think? Are these independent events? Ooh, we have some discord here. Think about this. You have a deck of 52 cards. You're going to draw the first, then you're going to put it back and shuffle the deck before you draw the second. So will the first card have any impact on the second card? No, because I'm replacing it, because I'm mixing it back up. So are these independent events? Yes, they are. So we're going to have the probability of drawing a king and then drawing a queen. Okay? Drawing a king and then a queen. So what is the probability of drawing a king? 4 out of 52. Very good. What's the probability of drawing a queen? Good, 4 out of 52. Now, some people, it makes more sense to them to simplify these fractions before they multiply them together. You're welcome to do that, or you can just put it in your calculator and simplify it. What do I get as a fraction? Very good, 1 out of 169. Okay, now that we have a firm understanding of independent events, let's discuss dependent events. Okay? On number 6, it talks about a dependent event is also referred to as selection without replacement. It means that the first event does impact the second event. So a really good example of this is number 5, where we talked about drawing a card, then replacing it and shuffling it, and then drawing another card. That is with replacement. But what if I don't put it back? What if we don't have replacement? That is called selection without replacement. So on number 6, it says, what is the probability of drawing a king, then a queen, from a standard deck of cards if the cards are drawn without replacement? Okay, so this is going to be the probability of drawing a king, then a queen without replacement. And this really changes things, okay? This really changes things. So the first card that we're going to draw, we want to get a king. What is the probability we're going to get the king? 4 out of 52. But now, when I go to draw the second card, I'm not going to put that king back. I'm still going to have it out. So, how many queens are still in my deck? 4. But how many cards are now in the stack? 51, because I didn't put that king back. Are we okay with that? So now I multiply that together and simplify it, and I get, very good. Now what's funny is if I were to turn this into a decimal and number 5 into the decimal, you'll notice that the decimals are both like about 0.006. They're both really, really close. So like not all of them have a huge impact, but it's still there. Okay? Now that leads me to probability law number 11. If two events, A and B, are dependent, then the probability of A intersection with B is the probability of A times the probability of B given A, which is the same thing as the probability of B times the probability of A given B. So look here, it's the same concept. We said the probability of my first event times the probability of B given A. So the probability of finding my queen given that I took out one of the kings. Same thing. So let's look at number 7. Assume there are 17 men and 24 women in the Lions Club. 2 members are chosen at random each year to serve on the hospitality committee. What is the probability of choosing 2 members at random and the first being a man and the second being a woman? So I want the probability of a man and a woman. What do we think? Is this going to be independent or dependent? Yeah, because we have without replacement. They're not putting the person back before they choose the second one. Okay? So they want to choose a man. How many men do we have? 17. Out of how many total people? 41. Now when they go to choose the woman, they have how many options? 40 options left, but how many of those options are women? 24. Okay? So it changes the denominator, and when you multiply those together and simplify, you should get 51 out of 205.